Hi, I want to go over a couple of the problems that are in that exam 3 simple that I sent you earlier. In the third problem, we have a block that's pushed against a spring, causing the spring to compress a distance of 0.075 meters. And then it's let go. A couple of things you should realize when doing this problem is that once the spring becomes uncompressed and gets back to its xb equal to 0, at that point the spring energy goes to 0, the spring potential energy goes to 0, and the block leaves the spring. So there's no more spring energy associated with the block once it leaves xb equals 0. So if we were to write a conservation of energy equation describing the motion, we would say that the work done by the friction, which we know is equal to F minus FKD, because the friction is acting in this direction as the block moves towards x equals 0. That work is equal to the change in the spring potential energy plus the change in the kinetic energy. And the second thing I want to point out is that the change in the potential spring kinetic energy is equal to 1/2 k x final, which in this case is xb, minus 1/2 k x a squared. And that this term is going to be equal to 0 plus delta k. So that's all I wanted to say about this problem. I hope you'll think about it before you take the exam. I also want to describe how one would approach question 4, which has a block that's pulled by a tension force to the right, a distance d, and experiences friction acting in the opposite direction during that displacement. In part A, we're asked to write a full conservation of energy statement for the block, assuming it starts from rest and ends with some final velocity v sub f. So here's how you would write that, just applying the energy principle. The work being done on the block is that due to the friction, to the tension, plus the work done by the friction. And that will cause a change in the kinetic energy. And to be complete, there would be a change in the potential energy. But in this case, there is no elastic potential energy, and the gravitational potential energy doesn't change. So this second term on the right is 0. And we could rewrite this work in terms of the forces involved. So the work done by the tension is the x component of the tension force, which is T cosine theta times the displacement D. And the work done by the friction is going to be equal to minus F sub K times D. And that's going to be equal to change in K. And that's a complete conservation of energy statement of this problem.